Okay, everybody, friends in person and friends on the Zoom. It is a distinct pleasure to have with us here today Professor Kohta Murase. Kohta did his undergraduate studies at the University of Tokyo and his PhD studies at Kyoto University. And then he moved to the United States. He was a CCAP fellow at Ohio State, and then he was a Hubble fellow at the Institute of Advanced Studies, and then moved to Penn State, where he has been serving since as an associate professor. He does all things cosmic rays, astroparticle, neutrinos, and today we will hear from him about the multi-messenger view of high-energy cosmic sources. So, Kohta, it's a great pleasure to have you.
Thank you very much for the kind introductions. So thank you very much for giving me an opportunity to give a talk. I have been enjoyed my stay here. This is the first time to visit Crete, and the food is excellent. I also visited Knossos and several sightseeing of several places for the sightseeing, and then that was well. Okay, that is excellent. Okay, so I'm very happy to talk about this exciting topic about the high energy neutrinos. Last year, this year, we have a very exciting news from the IceCube, which is the neutrino experiments they're detected in the Antarctica. And I'm going to talk about the recent results of the IceCube and discuss some theoretical implications in light of the Multimessenger astrophysics. Okay, let's start. Okay, good. So why we are interested in neutrinos? The neutrinos are electrical neutral leptons. They only interact with matter radiations only through the weak interactions. They are so-called ghost particles, and almost massless. And neutrinos are important in both astrophysics and particle physics. These are demonstrated by the Nobel Prizes. And in 2002, Nobel Prize went to the Koshiba's R.M. Davis Jr. and for the detecting the neutrinos from the supernova. And this happened more than 40 years ago, 1988. And also the neutrino detection from the sun. And this tells us what is going on, the very dense environments inside the stars. For example, in the case of superneutrinos, by detecting neutrinos, we learn that most of the gravitational energy is actually released by neutrinos. And then neutrinos also give us information on the particle physics, and it is also demonstrated by Nobel Prize in 2015. And the Super K experiment detects atmospheric neutrinos, and which are produced by the cosmic rays hit the atmosphere, and they found the neutrino oscillations, and which means that the neutrinos have mass. And then the solar neutrino experiments also lead to the discovery of neutrino oscillations, and these actually allow us to establish the neutrino has a mass, and this is also important for the studying the beyond the standard model. So okay, so when the Kajita-san and won the Nobel Prize in 2015, he says that I want to thank the neutrinos, of course, and since neutrinos are created by cosmic rays, I want to thank them too, because super experiments observe the atmospheric neutrinos. They are produced by cosmic rays. But the cosmic rays, okay, the cosmic rays also the cosmic rays energy charged particles coming from space. We know that they cause a problem in the softwares and the electric devices, or it also leads to the radiation exposure. And they play a very important role historically in the early times of particle physics. These actually are used for the discovering the pions, right? And they are regarded as the cosmic shifts, and they played very important roles in the both particle physics and astronomy. However, we don't fully understand the cosmic rays. So this is the spectrum of cosmic rays that we the observed cosmic rays over the wide energy range. And the spectrum of the cosmic rays observed on Earth can be described as power law distribution. Roughly speaking, the distribution is the index is 2.7, and but you can find if you look at the spectrum in very details, there's some structures steepening feature around the 3 PeV. 1 PeV corresponds to the tensor 15 electron volts, which is very high energy, and then around the several times tensor 18 electron volts. The tensor 18 electron volts corresponds to EeV, and then there's a hardening. It's very difficult to see in this figure, but there's actually a hardening. And then this high energy is actually the so-called ultra high energy cosmic rays. And the people believe that they are come from exotic sources. And then this, for example, the 3 times 10 to 20 electron volts that corresponds to 50 joules, which corresponds to kinetic energy of the tennis ball with 160 kilometer power. So just one particle has the very large energy, it's the microscopic energy. So such a ultra high cosmic rays, the question is that not so obvious to accelerate. So even our largest accelerator is Large Hadron Collider. And if you want to produce ultra high cosmic rays with LHC magnet, and then LHC has a maximum energy of about 30 GeV in the center of maximum energy. And if you want to make it larger, and you need the material orbit. Probably you don't want to make this, right? It's too big. It's very expensive. So even for the space, even if you go to the space, it's not so all easy to produce ultra high cosmic rays. And we believe that we need some monster accelerators. So one of the leading candidates is the so-called active galactic nuclei. And we call it AGN. So some of the galaxies have a very active a lot of activity in the center. And this is actually the famous picture of the MT7, and which is one of the galaxies in the center of this galaxy. And Event Horizon Telescope actually has an image of the black hole. And then we know that there's a supermassive black hole with a mass of 6.5 billion solar mass. And then from the black holes, we see the very large scale jet, the powerful jet. And the scale of the jet is about 5,000 light years. And this shows that the black hole is really active. And it actually also has the outflows and a lot of energy outputs to come from the black hole. So we believe that these kind of black holes, including the AGN, well, some people think about some jets that are produced by the quark corpuscles, massive stars, and which may lead to the neutron star black holes, the so-called gamma bursts. These jets can accelerate the particles to the very energies. In these very energetic accelerators, and the protons accelerated and the electrons accelerated, then we also see a lot of photons from these objects. These are so bright. And then if the cosmic ray protons and electrons are co-accelerated, then protons interact with photons because they are so bright. And then these photons provide target photons, and the photon interacts and produce pions. And charged pions eventually decay, and then we have neutrinos, and also gamma rays. And another scenario is that if you look at the galaxies or galaxy clusters, in this case, we have a lot of gas, right? In our nuclei, we have gas. If you go to look at this, and the cosmic rays actually is the wandering in then they are confined for a while. While they diffuse inside the galaxies or these kind of environments, they hit the gas, and again you can produce pions. And then charged pions lead to the production of neutrinos, and the neutron pions lead to the production of the gamma rays. So these kind of processes are responsible for the production of the high energy neutrinos and the gamma rays. So idea of the Multimessenger is as follows. So if you want to pin down the accelerator, the cosmic rays, of course, we can use cosmic rays themselves, but this is often challenging because of we don't know, we don't understand the magnetic fields. So they are easily intervened by the magnetic fields, and then not so obvious to locate the position of the astrophysical sources. So in this sense, neutrinos and the gamma rays are good, they are neutral. But the gamma rays actually also has a problem. So if you go to the very energetic gamma rays, these gamma rays start to interact with the ambient photons, and they cause gamma interactions, producing the electron positron. Then these electron positrons actually the kind of high energy gamma rays are kind of attenuated. We may not directly observe the high energy photons. But the neutrinos do not have a problem because they only interact with the matter with very interactions. So neutrinos enable us to see the distant universe invisible with gamma rays and ultra cosmic rays. So now we are in the exciting, the golden time of the multimessenger astrophysics. So that these are exciting times brought by the two discoveries. The one is the detection of gravitational waves, and the other is the detection of the high energy neutrinos. And then high energy neutrinos, 2013, the IceCube collaborations reported the evidence of the cosmic neutrinos. IceCube detector is located in the Antarctica South Pole. It was completed in 2010. And then they first provide the evidence in the 2013. The 17, they start to see some evidence for the neutrinos from the supermassive black holes. And then in the 2013, they basically observed the neutrinos from the sources in the old sky, basically all directions, all distances. They just observe the cumulative fluxes of the neutrinos. Okay, so neutrinos come from everywhere, and as the neutrino hits their ice, and then for example, when the muon neutrinos hit the ice, and the muons are produced, and the muons are propagate, and they deposit the energy, and by which you can detect neutrinos. In this case, we can have a factor of 2 energy resolutions, but muons actually leave a long track, and which is good for the angular localization. 1 degree, which is still bad compared to optical observations, but it's very good for the if you compare with the gravitational waves. And we also had channels, so-called showers. So the electron neutrinos interact with the ice and causing the electron, producing electrons with charge current interactions. Or all flavor neutrinos can interact with the ice and through the neutral current interactions. And in this case, we have a little bit good energy resolutions with 50%. But instead, because of a lot of photons scattered, and the angular resolution is poor. Typically, the angular resolution is 10 to 15 degrees in the case of showers. So we have these two channels, and IceCube is actually observed for the neutrinos for many years. And then this year, I think one of the big news was they finally start to see the evidence for the neutrinos from our Milky Way. So that we actually, in the optical, so that we have that we observe the Milky Way, and like this, and we have an image. And then the gamma rays, we see the Milky Way, radius. And now the IceCube collaborations are analyze the shower data, and using the machine learning technique, and they start to see the neutrinos from the image. Well, of course, this is still not, more vague, but this is the kind of the very important step, right? To study the galactic plane using the non-photon particles. Okay. So the neutron emission from the Milky Way is only 10% of total, and but still there we see the kind of evidence. So what can we learn from these neutrinos? And in this case, we now have a very promising connections between the neutrinos and gamma. So when the cosmic rays interact with gas, again, we have neutrinos and gamma rays. And in this sense, it's inevitable to produce a similar amount of the neutrinos and gamma rays. Okay, it's inevitable because of the particle physics nature. And the Milky Way is order of 10 kiloparsecs. Then most of the gamma rays can still reach the Earth. So in this case, okay, in the past, so if you look at more than 10 years ago, we have not observed gamma rays or neutrinos. But even at that time, we only had the upper limits on the gamma ray data. This is the gamma ray energy, and this is the energy flux of the gamma rays. We have upper limits. So because of the upper limits, you can convert the gamma rays flux to the neutrinos. This actually gamma ray upper limits can be converted to the upper limits of the neutrino flux. Based on these upper limits, we already know that the contribution of the galactic sources to the neutrino sky is already subdominant, even at that time. Then since then, the situation is changed. And just a couple of years ago, 2021, the Tibet gamma ray detectors actually start to see the diffuse gamma rays from the galactic plane. Here is we see that photons are concentrated in the prey. And then this is actually we have a gamma rays, and recently this year is the LASO, so it is the gamma detector in China. They also start to see the diffuse gamma rays from the galactic plane. Then we see the gamma rays in the diffuse gamma ray in the 10 TeV to 100 TeV range, and very high energy range. And again, if you see the gamma rays, you can convert the gamma ray flux to the neutrinos. So you can make a prediction of the neutrino flux from the galactic plane, assuming that these gamma rays are hadronic. Okay, and this is the kind of predictions of we convert the diffuse gamma rays from the Tibet data and the RAS data and to the neutrino flux. This is the kind of predicted of the hadronic scenario. And this is already consistent with the theoretical models, right? This is the model curves, these ones. But now, IceCube collaborations actually observes the diffuse neutrino flux of the galactic plane. Then if you overlay these predictions, unfortunately, this kind of data still depends on the templates, but you can see that the IceCube data, right, observed diffuse neutrino flux, actually they're very consistent with the predicted flux from the diffuse gamma ray data. So what that means that which suppose this consistency suppose that the diffuse gamma rays have a hadronic origin, producing PP interactions. And then that's actually also very important to understand what makes these diffuse gamma rays. And now the very important question is that now the Hawk and the LASOs start to see the pivotrons and or 100 TeV sources, and which contain a lot of the parts of wind nebula or possibly the supernova remnants. And interesting question is that observed neutrinos or these diffuse gamma rays are truly diffuse. Truly diffuse means that the cosmic rays are confined in the Milky Way produce neutrinos. So what are they confined? Okay. Or they might consist of the unresolved sources, superposition of unresolved sources. These are my kind of interesting questions, which can be addressed with the more future observations. Okay, so if we go back to the bulk of the neutrinos, so the important is the galactic contribution is still 10%. So that we don't know the rest. So if you look at the neutrino sky, and the overall distribution is consistent with the isotopic distribution, and which suggests the extragalactic origin. And the big question is that where do these neutrinos come from? Okay, it's kind of most efficient. Then people discuss the AGN or gamma bursts or galaxy clusters, which are the largest gravitational gravitational bound object and or starburst galaxies. And then these are the questions we'd like to address. And then neutrinos so far statistically limited. And in this case, it's very important to make use of the multi-messenger approaches. So let's look at the multi-messenger data. So this is again the energy flux of the all sky flux observed on Earth. So the x-axis is the energy, and the y-axis is the energy flux, which actually is implies the energy generation densities in the universe. So we have now neutrinos, and if you go to the ultra high energy, we have a cosmic radiator. And here is above 3 times 10 to the 18 electron meter above. These are ultra high cosmic rays, which actually is most likely the extragalactic origin. These are more likely galactic. And we have a gamma ray in the data from the Fermi in the sub-TeV range and the 100 GeV or GeV range. And if you look at the first glance, within the order magnitude, okay, you can see that even if the particle energy is very different, right, by more than 1 on the 10 on the magnitude the energy, the energy flux is actually more similar within the 1 order magnitude. So this implies that the energy generation densities of 3 messenger particles are actually all comparable, and you might think about connections, right? Maybe they may have a similar origins, or origins have a similar kinds of connections.
What's the horizontal line?
This is basically the Waxman around 3 times 10 to the minus 8, kind of benchmark level of the neutrinos. So basically, you see that these lines actually you see that all the energy flux is more or less comparable, just kind of the benchmark. Next question is that can we have such a unified scenario? The answer is yes. So this is one of the possibilities. And we can make some grand unifications because we are actually unifying 3 particles, right? So the ice cube neutrinos and the ultra high cosmic ray data and the gamma data, and in the diffuse gamma ray data, which is indicated in the gray range. In this sense, so actually this is specific scenario that we consider AGN as the ultra high cosmic ray sources. And then like this, so that we have cosmic ray sources as a AGN. We have AGN as a cosmic accelerator, and then low energy cosmic rays just diffuse inside the galaxy clusters as a reservoir, and hit a gas and produce pions by PV interactions. And we have pions, and then pion decays. You have neutrinos gamma rays, and neutrino gamma rays propagate. And ultra high cosmic rays actually is more easily escape from the galaxy clusters. They actually propagate, and then they can observe the image, or they can reach the Earth eventually. This is the kind of scenario. So, but in the gamma rays, we have to keep in mind, and one thing, and because as I told you in the beginning, so very energetic gamma rays cannot interact, cannot reach the Earth as they are because of the interaction with the accelerated background, right? So this is the mean free burst of the gamma rays in the other energy. So that if you go to the PeV, 1 PeV, gamma rays only propagates 10 kiloparsec. And in the TeV range, 1 TeV range, 10 to 20 electron volts, the gamma rays propagated only a few hundred megaparsec. Okay. So that if you go think about the very distant universe, like gigaparsec, or redshift 1 or 2, and in that case, these gamma rays actually interact with photons and the background radiation fields, and then eventually you have electron photons. But the important is these electron photons are still very energetic, and they keep interacting with the ambient photons and by inverse Compton scattering. And then we have this kind of process can repeat, which is so-called electromagnetic cascades. And eventually, even if you have a very energetic gamma rays in the TeV or PV, these gamma rays cascaded down, regenerated as a GeV or TeV, sub-GeV gamma rays, sub-TeV gamma rays. So that's the reason why. So that if you look at this growth and the neutrinos here, but gamma rays actually already cascaded down to the sub-TeV range and observed as a GeV or 100 GeV energy range. And then this also good that because we can explain why the gamma ray flux and neutrino flux should be comparable, right? Because this you are just putting the energy here, just cut it down, and energy conservation. Okay, so far then everything sounds good, right? If you have a grandification, that's nice. However, the probably real story is not so simple. Okay, this is a kind of updated plot of the multi-messenger flux. Okay. Okay, so well, if you look at the data, neutrino data very carefully, okay, then we see that neutrino flux is actually the higher if you go down to the 10 TeV range. Actually, the neutrino flux is actually around 10 to the -7 or something like that. So here is actually around the 2 times 10 to the -8, right? And then this is actually 10 to the -7. It's actually neutrino flux is very extended to low energies and with a higher flux. And actually, this is it. So, okay, so that you probably understand the connection between neutrinos and gamma rays, which is unavoidable, right? Just this is context on the particle production, particle physics. So then let's step back and then we can think about the connection between neutrinos and gamma rays again. So here, this is the neutrino data in the 10 TeV. You want to explain that these neutrino data either PP or P gamma. Either case is fine. But if you assume that gamma rays escape to the source and just propagate in the intergalactic space, again, this process is actually called electromagnetic cascades. They eventually cascade down to this energy range. If you normalize the neutrino flux with the current ISQ data in the 10 TeV range, basically expected gamma ray flux is overshoots the non-Blazer component of the diffuser background. This is a problem. So that we can actually demonstrate that this kind of problem in this kind of plot. Here is a spectrum index, and this is a flux. So this data is actually this data. Let's look at this green data. Okay, this is the best fit flux of the neutrinos ISQ data here, and then the gamma limits already put the upper limits like this. And you see that tension between the neutrino data and the upper limits for the gamma is actually about more than 3 sigma. And this tension is even worse if you consider the other component, right? Because the gamma ray flux may come from the other more sources, like the star-forming galaxies or whatever, the leptonic contributions. The this tension is actually increased. So this is a problem. So that this implies that probably the assumption that the gamma rays escape the source is wrong. So that this suggests that we need this suggests the existence of hidden sources in the sense that gamma rays in which the gamma rays are actually blocked inside the sources. Like the question is this natural or strange? I would say that this is natural because if you think about the P gamma interactions. Okay, let's think of the P gamma interaction. And in this case, in order to produce the neutrinos, you need target photons, right? P gamma interaction, because of proton interacts photons, you need target photons. But these same target photons are also dangerous to the very energy gamma rays. Because the inside sources, you need the photons to reach neutrinos. These photons also kill the gamma rays by the gamma-gamma interactions. So that if you compare the cross-section of the gamma-gamma interaction to the P-gamma interaction, the cross-section ratio is about 1,000. So this means that if you want to have a good efficiency of the neutrino production, and then automatically the gamma-gamma interactions should also be efficient, and which means that the gamma rays actually can be easily blocked inside the sources. So this is naturally possible, and which kind of sources can do that? And then of course, you can think about different possibilities, but probably one of the most promising source population is AGN, especially in the vicinity of supermassive black hole. Because if you look at the AGN, we have a black hole and the gas accretes and gas formed accretion disk. And accretion disk emits the optical photons and in the ultraviolet photons. And we have a corona, which is consists of very high temperature regions, and then the X-rays. This in the vicinity of the corona, and then the gamma rays naturally blocked by the gamma interactions. Neutrino production can be very efficient. Indeed, if you want to compute the neutrinos from this AGN, it's possible to explain the 10 TeV neutrinos. And the gamma is actually already cascaded down inside the sources rather than outside sources. And then the gamma is actually appear in the much lower energies that we don't have to violate the Fermi gamma vacuum. So that's nice. And then now but the question is that do such hidden neutrino sources and exist? The answer may be yes. So the last year, so the ASCII collaboration reported the evidence for the neutrino emission from the nearby active galaxy, and she 1068. And she takes it's located at the distance of the 10 megaparsec, which is one of the most famous Cepheid galaxies, have two. And a lot of gas and dust exist. And indeed, this is the kind of infrared image. And then we actually the infrared they have some localized location dust towers. So in this case, okay, this is ASCII data. The ASCII collaborations look for the neutrinos using the 10 years of data, and they selected the source cut. They basically prepare the source catalogs that are about 180 sources, and then they search for the hotspot. And it turns out the most significant hotspot is coincide with the location in 1068. And we indeed this plot we see the 80 excess events, and which corresponds to the 4.2 sigma as the post trial. So this is the energy flux. This is the energy of neutrinos, and this is the energy flux. So here is this blue shaded region, the ASCII flux. And indeed, as I told you, so the neutrino flux is actually much larger than the Fermi gamma ray flux or upper limits by the magic telescope. So this indeed supports the hidden sources, right? Because neutrino flux is larger than the gamma ray flux. Okay, hidden source. Because, for example, if the think about the starburst galaxies. NH10 actually is also known to be the starburst galaxy. In this case, neutrino flux and the gamma ray flux should be comparable because the gamma ray should escape. If you assume this, because gamma ray flux is observed, neutrino flux is also similar, and then you cannot explain the data. So the starburst galaxy model cannot explain this. So this means that you probably need to think about the more inner regions. If the neutrinos are produced in about such a really far regions, it's difficult. And if you go to that across the black holes, then you can avoid this kind of problem. Let's quantify this kind of argument. So where do neutrinos come from? So the good thing that for this ancient X-rays, we have information from the X-rays. So the new stars observes X-rays, and we have information of the X-ray luminosity. So which is the order of a few times 10⁻43 erg per second. Okay, we know the X-ray luminosity, and you can estimate the gamma optical depth. So we know the cross section, we know the X-ray luminosity, and then the parameter is the radius, right? The emission, the radius, right? So the distance from the black hole. So if the radius is actually too large and the optical depth is low, and a problem because gamma is actually produced a lot. So that in order to hide the gamma rays, that this optical depth has to be larger than 10, or something like that. And this situation can be demonstrated by this kind of plot. Okay, so the actual argument is very similar to what I did for diffuse neutrinos gamma. If you want to explain neutrinos, and then gamma is actually produced, if the emission radius is very large, say the 10⁻⁴ radius, and then the gamma ray flux is about the Fermi data. And if the radius is so small, and then the gamma optical depth is larger, and this is actually shifted to lower energy, and if the emission radius is very small, smaller than say 30⁻³ or 100⁻³ radius, and then you can avoid the vibration. You don't have to vibrate the Fermi gamma radiation. So this means that in order to produce neutrinos without vibrating the gamma ray data, so the neutrinos must be created should be created in the very disintegrated black hole. And this is good for the in light of the neutrino productions, because once you go down to this kind of small emission radius, and neutrino production efficiency is very high. And basically, if you produce a cosmic rays are very efficiently depleted for the pion production. And a kind of idea that we can regard the black hole as a kind of idea of the beam damp. So, okay, so that's a kind of general argument. Then next question is that where the particles accelerated. This is the open question. So the people think about the different possibilities, and then basically you can think about shocks. Maybe we have the wind and with actually the fallback and then causing the shocks, maybe. But probably the most promising scenario is the corona. So now the different simulations suggest that when the gas accretes on the black hole, that we have the formation of the accretion disk. In the above the accretion disk, we have a kind of very high temperature regions, and high temperature, the magnetic dominant regions is corona. So in the corona regions, magnetic fields are very strong, and the reconnection happen, and we also have a lot of turbulence, which is actually very promising as a particle acceleration sites. So in the case of the particle acceleration mechanisms are also unknown, but if you have turbulence, then we can expect some Fermi acceleration. So this original Fermi acceleration is that we have turbulence instead of the clouds, and we have a turbulence, and then in this case the particles can be scattered by these turbulence. And they can gain the energy, and they can get the net energy gain. And in this case, the particle can be accelerated by through the random scattering. So this is good. The acceleration is relatively slow. And if you think about the acceleration time scale here, this x-axis is the particle energy, and the y-axis is the time scale. And if you have in the vicinity of the supermassive black holes, we have a lot of X-rays, and then we have P-gamma interactions, and not only P-gamma interactions, but also the base Hiter process, the P-gamma interactions and P-gamma, and producing the electron-proton pair production is very important in the 100 TeV range. And if you compare the acceleration time scale and these cooling time scales, you can determine the maximum energy. And if you compare the stochastic acceleration, the time scale, and this base Hiter time scale, the maximum energy of protons is around 100 TeV, and which corresponds to the energy of neutrinos about 20 TeV, which is actually more or less similar to the energy range of the neutrinos. So in a sense, kind of stochastic acceleration scenarios are also kind of compatible with the observations of the ice cube. Now, if you think about very fast accelerations or shock acceleration deconnections, typically the acceleration time scale is very fast, and the maximum energy is typically higher. So you need to think about the mechanism to reduce the maximum energy. Okay. So nice thing is that this kind of particle acceleration turbulence has been studied by the recent simulations. And then now I just demonstrate a couple of simulations, and then now we can do the global image simulations. We can actually have generated turbulence, and then you can inject the particles and perform the test particle simulations. Indeed, we can see the particle accelerations and based on simulations. This is the kind of study that just still is a kind of preliminary. We need more investigations, but hydrogen neutrinos, this demonstrates that hydrogen neutrinos now meets the kind of frontier of the astroplasma physics. Okay, so now let's think about go back to the current situation. So do we have more hints of these neutrinos? And the answer is actually yes. So I already showed that the two example of energy 1068, but it's quite natural to ask that do we have a different evidence from the other AGN? And now as we look for the other sources, there's actually the possible access towards the other AGN, including the NC 4151. They also look for the kind of stacking analysis that based on the infrared selected AGN. They also have some kind of access. So good news is that we have hints, and good news is that now the other neutrino telescopes and then coming, the BICAR and the chemistry net. And once we have a chemistry net, then this is this kind of the model is kind of the sources can be testable. Now, for example, this plot actually shows this kind of testability. And if we have a chemistry net, and the angular resolution is supposed to be good, and we can see the neutrinos from these AGN within a few years. And then as keep going to be upgraded, and we have a Gen 2. Again, the Gen 2, we have more statistics, and it's possible to test this kind of scenarios within a few years. Another important test is gammas. So I told you that, okay, so the neutrinos produced and the gamma rays are created, and the gamma rays actually eventually cascade down into the sources. This is the spectrum of the energy 1068, the same source, energy 1068. And then, but the gamma rays, important point is the gamma rays are not gone, right? Because of energy conservation. They should eventually appear in harmony. And not TeV or PeV, but they are predicted to appear in the MeV or sub-GeV range. So here is actually approach. So we look actually to analyze the Fermi data, and then we found that if you look at the sub-GeV region, and we found some excess. This is the excess is actually the excess compared to the prediction of the pi zero band, because GB or higher energy gamma ray components are believed to come from star forming activities in this case, in this source. And then yes, this starburst activity can explain the gamma data, but obviously we have found a component which cannot be explained in this guy, and this excess component does not have to be can be anything, but interestingly, corona model predicts that these gammas eventually cascaded down to this MeV component, and this excess emission is indeed consistent with the prediction of the corona model. So this is a very encouraging. So that we have already hints in the gamma data of the coronal emission. If this is the case, it's very important to look down to the MeV range. Now, unfortunately, we don't have a good gamma ray telescope in the MeV range. And we probably, if we have a good MeV telescopes, there are some proposals like including Astrophysics, Amico-X. We have a good MeV telescope that we can test this scenario. Okay, how about the other AGN? The prediction of this kind of corona model is that neutrino bright AGN should be extra bright AGN. So interestingly, the NC 1068 is actually predicted to be the brightest in the ice cube sky, and the second brightest is actually the NC 4151. And we look for the data and the gamma ray data, and then we don't see any gamma rays in the Fermi data in the NC 4151. But this model is still compatible with these upper limits, and a similar model to explain the NC 1068 also that can explain the NC 4151 neutrino access. And if the model also predicts that there were more bright agents in the southern sky, which is very encouraging for the chemistry net. And then the most promising sources include NC49, 45, 45, and the sustenance. And in the case of NC49, 41, we analyze the family data, and this gamma is here. And we also have the sub-GeV excess, which is similar to the NC, which can be consistent with the current model, which is also kind of interesting hint. Okay. Now that I'm using the 10 minutes, I'm going to discuss transient. So for transients, like a flares, we have the advantage because of the pointing and timing. So that if you have a timing information, okay, here is the background, and which consists of the atmospheric neutrino background. But if you have a timing information, so we can effectively reduce the background. You can actually dig out the signals. So primary source is this source, the TXS 0506. So in 2070, and then the ISQ detected very energetic neutrinos with the energy of about 300 TeV. And then they look at the direction of these ISQ neutrino events. They found the flares in the different wavelengths, from radios, optical, the X-rays, gamma rays. And then the counterparts, you can compute the coincidence significance, which is about 3 sigma. And even more, the ISQ corporation look at the archival data, and in the archival data analyze and data in the 2014-15, they found the flare, neutrino flare, and excess of the certain events. However, this flare does not have electromagnetic flares. So if you look at the gamma ray data, sorry, here gamma ray, X-rays, and radio, there's no indication of the flaring activities. On the flaring happening only neutrinos. So this kind of TXS, the jetted agent, the brazier, but still you can play the similar game. So if neutrinos are produced by the pigment interactions, you have neutrinos, and the gamma ray electrons, positrons should be cascaded down into the lower energies. And if you want to explain the ISQ data, and for example, in this case, okay, so in this case, we have a very beautiful X-ray data, and in order to not violate the X-ray data, the neutrino flux must be small. Because if neutrino flux is high, you violate the X-ray data. And this actually the constraints the model. And then basically, if you want to satisfy the electromagnetic observations, neutrino flux cannot be too high. And if you want to match the neutrino data to the observed flux levels, that you violate the electromagnetic data. So that's a problem, that we have a tension between the theory and the observations. So the situation is that very unclear. So we don't know that at least a simple model doesn't work to explain the neutrinos from this jetted agent. So this means that it's very important to look for the more indications, right? And then do we have more coincidences? The answer is actually yes. So we have a couple more coincidences, but unfortunately the story is actually similar. And we are not, the situation is very unclear. And then, but people also try to look for the coincidences with not only braziers, but also the optical transients. And then basically what people did is that, the neutrinos are detected in the ISQ, and they look for the transients in the optical sky, and for example, using the ZTF. And then interestingly, they actually, people found that some long duration optical transients with a duration of the months to years have been found. Then which usually interpreted the tidal disruption events, and then accelerator, and then this is the optical transient found before the peak was actually the high. The peak is actually before the detection time of the neutrinos. Then otherwise, actually, the neutrinos actually delayed compared to the optical peak, with the time delay of 150 to 300 years. So far, we have about 3 to 5 optical candidates are reported, and then all of them are rare optical charges with a strong infrared echoes. but the significance is not so high. And then again, the story is actually situation are not clear. But theoretically, it's kind of interesting to think about neutrino emission from this kind of event. So people believe that this long duration optical transients at tidal selection events, so that when the supermassive bulk exists and the star is approaching and the star is disrupted, and about half of the star material goes away, and the other half actually eventually returns and then forming dissipates, and a part of the material that forms action disk, and you have winds or possibly jet. Okay. So you can apply the similar neutrino mechanism for the AGN to this kind of TDE process, right? And then neutrinos can be produced by the corona, or maybe the produced in jet or wind. And it's interestingly, these kind of the neutrino events, which are observed from these optical transients, can be explained by assuming the similar mechanism for the use for the AGN. So that maybe the common mechanism may operate. And this is but statistically, it's not so clear. It's very important to have more observations. And here is probably one of the important information is the extra observations. And when the neutrinos observed, and again, there's neutrinos, the gamma is eventually cascaded down, and the lower energies, and then in the harder X-ray to the MeV energy range. So that if you have a good follow-up observations in the X-rays, and then this kind of the model can be constrained, depending on the quantum density you have. So the if you have a don't see the X-ray, we can put the strong constraint, or maybe you could have some emission. So this can be X-ray observations. X-ray follow-up observation is very important for testing the model. Also, once we have the Vera Rubin observatory, and we have the statistical TVs that increase a lot. And in this case, okay, we can do the actually more systematic surveys studies for the neutrinos from TVs. That's kind of promising. Okay, this is a summary of the current situations. Now the ice cube, have some interesting hints of the neutrino emissions from the supermassive black holes. In the case of the AGN, like I mentioned, we have some reasonable picture, and it's reasonable, and then we have some concordance. In the case of jetted AGN, and simple model doesn't work, and you need to think about the more complicated ESF observation too. And TDA is also case possible, but in this case is actually statistically not convincing. So definitely we need more search. Then we need more studies. Okay. I still have 10 minutes, so that if you want, I can actually talk about the implications of BSM searches. But if actually I can stop here, then I can actually have more questions. Which do you prefer?
I have a little question.
Okay. Okay, then I will go to summary in this case. Okay, so I think that we have a kind of bright future. Okay, so definitely in order to test this kind of situation, we have more statistics and ISQ-Gen2 and the chemistry net, the bioactivity, these kind of telescopes, neutron detectors will be very important to test the confirm or falsify the scenario and have more statistics. And if you are interested in the ultra-high energy neutrinos and ultra-high energy cosmic rays, we need to expand. We need to look for the neutrinos at the very high energies, even above PeV. In this case, Gen 2 or even the radio neutron detectors like GRAND will play an important role. And then for transients, so the gamma ray observations are very important. I would say that if you want to test the AGN or TD scenario, it's very important to have good information in the MeV range, which has not been covered by the existing telescopes with the good sensitivities. For transients, once we have better Rubin observatories, we can actually more samples, which is very important for this, especially for the tidal solution events. So here's a summary. So I showed that the multi-messenger approaches are very successful. And I still actually now the STV collaborations have the interesting observation from the galactic plane. We see the good multi-messenger connections between the diffuse neutrinos gamma rays. And then extratic neutrinos, multi-messenger analysis between the diffuse neutrinos and gamma rays require the hidden sources. And this is a prediction of which is actually now supported by the observation of the neutrinos from the energy-intensive state. And if this signal is true, and we can use the neutrinos as a unique probe of the high energy phenomenon and powered by black holes. And now the theoretical studies in this kind of coronary environments, the black hole accretions are very active, and which can be confronted with state-of-art theoretical simulations. And then it's very important to think about synergies with the brand MB gamma ray and the neutrino detectors. And for transients, we have several coincidences with black hole flares, including the blazer flares and heteroception events. Statistically, it's hard to say. We need more data, and we need more strategic multimedia searches. And I don't talk about this, and that's my talks. So thank you very much.
Questions for Kohta?
So you saw the slide where you compared the gamma ray with neutrino fluxes. And was this for one single object or for the general background?
Oh, actually, I did the both. And yes, actually, so the first plot is for the diffuse, means that all the fluxes. Okay, so basically I repeated. Basically, I did this argument for the both total all sky flux. This is a kind of comparison.
Yeah, it was towards the end of your talk.
Yeah.
So the question is really, if it's so that was the model. So if it's for the entire population of AGN, what model did you use for the population of AGN? And because
this is a model independent, because no matter what you did, right? Because just I use the data. I don't specify the sources AGN or not, because this is the we observe neutrinos, and no matter what they do, the neutrinos actually, these neutrinos actually are produced by the line of sight integral.
okay, what I'm talking about is not this one. It's towards the end of your talk.
Oh, okay. So this is actually the specific one. Probably this one.
Yeah.
Okay, this one is a specific source, one single object. Yes.
So the question is, if you calculate theoretically, assuming that you have an AGN population.
Oh, this does not need a population because this is only one source.
Yeah, assuming that you have a population,
yes,
and you start from the gamma ray flux, can you reproduce correctly the neutrino flux that you are measuring, or you are overproducing? I'm talking about mostly about the hidden AGN.
Oh, yes.
If you have too many hidden AGN, would you overproduce the neutrino flux?
It's actually possible. That's a very kind of important question. But this model that to produce neutrinos originally invented to explain the AGN.
Mm-hmm.
So basically within one of the magnitudes, it's possible to reproduce the diffuse neutrino. Yes. So that's possible to explain the energy intensity diffuse flux in the same parameter, like a similar model, within the same frame.
Okay, and we can talk about this line later.
Yes. So this is actually here. Yes.
But let me also follow up, because I was also wondering what Andreas is talking about with a different twist. You're showing energies that go down to MeV.
Yes.
But eventually, if you keep going down, you hit X-rays.
Mm-hmm.
And then all these hidden AGN that can in principle produce neutrinos. I mean, you have a garden variety AGN, nothing is going to stop it from producing neutrinos in that way. So you have limits on those from the X-ray pattern.
Exactly, this is what I was getting at.
Yes,
But
so can you at the same time explain neutrinos and the X-ray pattern?
X binary.
X-ray background.
Background, yeah, X background, yes, because actually this kind of population models actually that are this model actually that use the X agent populations which already reproduce the X background.
All right.
So in that
the
sense,
X-ray
automatic,
treatment,
So
but-
the anchored one.
yeah, so because basically I already use the luminosity function agent, which is actually already developed to extend X-ray background. So the automatically this actually consistent with the X-ray background. And then the canonical MEB gamma ray, but of course much lower than the X-ray background. X-ray is just counter column. So the basically this means that this kind of models predicts that because we use the population of the AGN model, which reproduce the X-ray background, that this kind of AGN can explain the X-ray background, neutrino background, and possibly the MEB background.
Other questions? Yes. Are there any online? I will look. Online people, if you have questions, please just unmute yourself and ask. I don't see any. Any other questions here? I have a comment. It is very interesting to me. We have been talking about multi-messenger approach to all these problems, right? And for example, neutrino astrophysics has been celebrated as a way to probe the hadronic accelerators in a way that doesn't deflect and so forth. But from your discussion, what I'm getting is that yes, the multi-messenger approach is extremely important, but for completely different reasons than we originally thought, right? Because it looks like there is a different population making the other kinds of rays. And these do not make neutrinos or gamma rays, because that would mean too much losses. And then there is a different population making neutrinos, which is a lot of losses, so that you make enough neutrinos to see them. And then there's a different population making the gamma rays, because then you need a little bit of losses to make gamma rays, but not enough losses to dump the gamma rays, which would give you neutrinos. So now, indeed, we have multi-messenger constraints, but they have separated the sources of these different messengers instead of unifying.
Yeah, but that's actually not surprising because when
No,
you
I
have
agree,
yeah,
yes.
if we have a existing neutrino sources, automatically the optical depth shall be variable.
Exactly, yes.
But still energy conservation is applies. When you say gamma rays, it's kind of dangerous to just focus on the very high energy gamma rays. So we also need to look for the MEB, the low energy gamma rays. So in that sense, the gamma ray neutrino connection does not have to be direct. In the galactic case, indeed, we see the direct connection, but in the external cases, because the source population has to be, source is more likely to be luminous, right? If you start to think about very violence, the monsters object, then this kind of connection can be, a bit more complicated, but still exists, right? That's the reason why we need to correct a lot of information, right? Then it's not direct, but this can be more fun in the sense that we need to collect different pieces of the information, and then that's actually the more useful to understand what's going on, especially this thing of supermassive black holes, or this is probably true in the other external sources.
I have many questions, but I will take them offline. Anything else from the audience? Okay, if not, let's thank Kohta very much.